There are three main topics that you talk about in calculus: limits, derivatives, and integrals. And so far in this class, we've talked about limits and derivatives, and now we're going to talk about integrals. Now, the topic of integrals can be subdivided into two topics. We have indefinite integrals, or antiderivatives, and definite integrals. Now, we'll talk about definite integrals later, but for right now, we're going to talk about indefinite integrals, or antiderivatives. That's what we'll talk about in this video. So let's begin with an example. Find a function whose derivative is x to the fourth. Now, I'm not asking what's the derivative of x to the fourth, right? That would be 4x cubed. I'm asking to find a function whose derivative is x to the fourth. So I'm asking for the antiderivative of x to the fourth. So we want to find a function where if we take the derivative of it, we get x to the fourth. So how can we do that? Well, one thought might be, why don't we take something like x to the fifth? Isn't the derivative of x to the fifth x to the fourth? Well, the derivative of x to the fifth would be 5x to the fourth. So maybe to kind of compensate for that, instead of using x to the fifth, could we use 1/5 x to the fifth? If we took the derivative of this, wouldn't that give us x to the fourth? Because the derivative of this, the 5 would come out front. 5 times 1/5 is just 1. The power would lower by 1. And yeah, that would give us 1/4. So notice the derivative with respect to x of 1/5 x to the fifth is x to the fourth. So 1/5 x to the fifth is called an antiderivative of x to the fourth. Now, it's not the only antiderivative of x to the fourth, because we could always just add a constant. So for example, plus 7. 1/5 x to the fifth plus 7, that would be an antiderivative of x to the fourth. And in fact, we could add any constant. But it turns out that any two antiderivatives are going to differ by a constant. So the general form of an antiderivative of x to the fourth would be 1/5 x to the fifth plus c. And we often use this letter c. It's called the constant of integration. So this is the general form of the antiderivative of x to the fourth. And just like we had a special notation that we use for derivatives, so we use like f prime for a derivative or d dx, well, we also have a special notation for integrals. And the notation that we use is this. We use this kind of strange looking symbol. It looks like an elongated S here. This is called the integral symbol. We have the integral of x to the fourth dx. And whenever you see an integral symbol, there'll always be a dx on the end here. And this is the function that we're integrating, x to the fourth. The integral of x to the fourth dx is 1/5 x to the fifth plus c. So this is called an integral symbol. The function that we're integrating is called the integrand. Okay, integrand. And this is sometimes called the differential, but you don't really need to worry about that terminology for now. The way that we say this is the integral, or antiderivative, of x to the fourth is equal to 1/5 x to the fifth plus c. So let's do this example. What's the integral of x to the seventh dx? So in other words, what's the antiderivative of x to the seventh, or the general form of the antiderivative of x to the seventh? Well, wouldn't it be 1/8 x to the eighth plus c? Now, another way to write this would be x to the eighth over 8 plus c. But 1/8 x to the eighth plus c, or x to the 8 over 8 plus c, that's the general form of the antiderivative. Now, we need the plus c here because this integral is not just asking us for one antiderivative, it's asking us for the general form. So you're always going to need to have the plus c on the end here. This brings us to the power rule for integrals. Now, remember, we had a power rule for derivatives. The power rule for derivatives told us how to take the derivative of x to the n. The power rule for integrals tells us how to do the integral of x to the n. The integral of x to the n is 1 over n plus 1 times x to the n plus 1 plus c. Okay, or in other words, x to the n plus 1 over n plus 1 plus c. And this works for every n except n equals -1. And this is actually kind of an important exception. If n is -1, then we'd be dividing by 0 here. But for any other n, we can use the power rule. So let's do a few examples. Evaluate the integral, or compute the integral. What's the integral of x squared dx? Well, the integral is going to be 1/3 x cubed plus c. Or another way to write that would be x to the third over 3 plus c. In fact, I kind of like writing it this way instead. All right, what about the integral of the square root of x? Can we do that here? Well, yeah, remember the square root of x is the same thing as x to the 1/2 power. And so here we're going to let our n be 1/2. Now, we always increase that number by 1 and then divide by the number. So the integral of x squared was x cubed, and then we divide by that number 3. So what's the integral of x to the 1/2? Well, we raise that number up by 1. X to the, 1/2 plus 1 would be 3/2, and then divide by 3/2 plus c. And that's our answer, but we can rewrite this. When you divide by a number down here, divide by a fraction, you can actually just multiply out front by its reciprocal. So dividing by 3 halves like multiplying out front by 2/3. So it's 2/3 x to the 3 halves plus c. That's the integral of the square root of x. And you can check if you took the derivative of this, well, the derivative of c just is 0. That goes away. What's the derivative of this? Well, wouldn't this 3 halves come out front? And 3 halves times 2/3, that's just 1. Then this number would lower by 1. Well, what's 3 halves minus 1? It's 1 half. So the derivative of this would just end up being 1x to the 1 half, or in other words, the square root of x. Now, what about this? What's the integral of 1 over x to the 6th? Well, again, let's rewrite this as x to the negative 6th power. That's what 1 over x to the 6th is. And we're going to use the power rule. Well, again, we always raise this number up by 1. So to raise negative 6 by 1, though, you're not going to get negative 7. You're going to get negative 5. And then you'll divide by that same number, negative 5. So x to the negative 5th over negative 5 plus c. Now, you could rewrite this. This negative in the denominator can come out front. This x to the negative 5th in the numerator can become an x to the positive 5th in the denominator. So we could write this as negative 1 over 5x to the 5th plus c. But it's totally fine if you leave your answer like this. Okay, now what about the integral of just x? Well, x is the same thing as x to the 1. The integral of x to the 1 would be x squared over 2, or 1 half x squared plus c. And again, you can check if you took the derivative of this, the 2 would come up front. The 2 over 2 would just become a 1. And lower that by 1, we're just going to end up getting an x here. And the derivative of c, again, is of course just 0. Now, what about something like just the integral of 7? Okay, what's a function where if you took the derivative of it, you get 7? Well, wouldn't it be just 7x? Isn't the derivative of 7x 7? In fact, we do need to add the plus c on the end here. 7x plus c. So like 7x plus 5, 7x plus 1, 7x minus 8. Any of those functions, if you took the derivative, you would get 7. So that brings us to this rule, the integral of a constant. Well, for any constant k, the integral of k dx is going to be kx plus c. So as a quick example, the integral of negative 3 would be negative 3x plus c. Okay, now what about something like this? We have the integral of x cubed plus x. Now, remember that for derivatives, we had that the derivative of the sum of two functions was equal to the sum of the derivatives. So it turns out for integrals, we have the same thing. The integral of the sum is equal to the sum of the integrals. So in other words, if we want to find the integral of x cubed plus x, we can just do the integral of x cubed and then plus the integral of x. And the integral of x cubed is x to the 4th over 4. And the integral of x, or x to the 1, is x squared over 2. And we put our plus c on the end. So there is our answer. Now, we could have done this by rewriting this as two separate integrals. The integral of x cubed dx plus the integral of x dx. And then say, well, the integral of x cubed is x to the 4th over 4 plus c. And the integral of x is x squared over 2 plus c. But the thing is, notice we end up with two constants on the end here. And actually, the two constants, you might think, well, that's just 2c. But actually, 2c is still just a constant. So usually we don't end up writing the constant twice. We just write it once. In fact, the correct way to do this is to just write it as x to the 4th over 4 plus x squared over 2 plus c. And you don't have to put a c plus c. You don't have to put 2c, because ultimately we just need one constant on the end there. But notice either way worked. I could either break it apart into two separate integrals here, right, as the integral of the sum, or just kind of do it one by one here. So we have a theorem here that says that the integral of the sum of two functions is equal to the sum of the integrals, and it also works for differences. Integral of the difference is equal to the difference of the integrals. And we're going to use this over and over again. Now, this is written for just the sum of two functions, but this would work if you had 3 or 4 or 5 functions. Any number of functions that are being added or subtracted together, you can do the integral of the sum as the sum of the integrals, and same thing with differences. So let's do a few examples. What's the integral of x to the 4th plus x to the 12th? Well, it's just going to be the integral of x to the 4th, which is x to the 5th over 5, plus the integral of x to the 12th, which is x to the 13th over 13. And we don't need to put a plus c and another plus c. We just put 1 plus c on the end here. Now, let's remember what we're doing here. The way that we would check our answer, the way that we check to see if we have the correct answer is we would take the derivative of this, right? We're trying to find the antiderivative of this and we're claiming it's this. How could we check our answer? Well, if we took the derivative of this, we should end up getting this. Now, the derivative of the c is always just going to be 0. The derivative of x to the 5th over 5, you can check. The derivative will be x to the 4th. And the derivative of x to the 13th over 13, if you check, you can see the derivative will be x to the 12th. So it's always possible to check your answer just by taking the derivative of your answer, and you should get the original integrand. How about something like this? Well, for this one, we have a cube root of x, so I want to rewrite this as x to the 1/3 power. And we also have a 1 over x to the 7th, so let's write that as x to the -7th. And we have a minus x, or you could write it as x to the 1, plus 1/4 dx. So what is the integral going to be? So we have this big long integrand here, and we're adding and subtracting several terms here. Well, what's the integral of x to the 1/3? Well, we always have to raise this number up by 1. So the integral of x to the 1/3 will be x to the 1/3 plus 1, which is 4/3, over 4/3, plus, well, the integral of x to the -7th is going to be x to the negative, and it's tempting to say -8. But if you raise -7 by 1, you actually get -6. Right? If you do -7 plus 1, you actually get -6 over -6 minus x squared over 2 plus, well, what's the integral of 1/4? 1/4 is just a constant, so it's 1/4 x plus c. And this is perfectly fine to leave your answer like this, but let's rewrite this. This 4/3 in the denominator can become a 3/4 out front. 3/4 x to the 4/3. Well, we have plus this, but this minus can come out front. So we'll just put this minus out front here. And this x to the -6 can become an x to the +6 in the denominator. And we have minus 1/2 x squared, or x squared over 2, plus 1/4 x plus c. So this is the simplified version of the answer. And sometimes if you're doing a multiple choice question, for example, you may do the integral, but it may not show the answer that you found as one of the possible answers. And the reason is you just have to simplify this sum, and then your answer should hopefully show up as one of the possible answers on that multiple choice question. Now, moving on, how do we do something like this? This is not just the integral of x cubed, it's the integral of 5x cubed. Well, just like when you do a derivative of a constant times a function, you get the constant times the derivative. The constant just kind of comes along for the ride. Same thing with integrals. The integral of 5x cubed is just going to be 5x to the 4th over 4. In fact, you can pull the constant out in front if you want. You can actually bring this 5 out in front of the integral and rewrite this. But the way to think about this is the integral of 5x cubed is actually just 5x to the 4th over 4 plus c, and that's the answer. Now, you could do this by actually pulling this 5 out front. So if it's 5 times everything else in there, you can bring the 5 out front and write this as 5 times the integral of x cubed dx. And then write this as 5 times x to the 4th over 4 plus c. Now, it might be tempting to say, well, let's put parentheses around this and then distribute the 5 and we'll get a 5c. But again, remember the constant on the end, just call it c. Don't call it 5c or 2c. The point is, if you do it like this, you should still get the 5x to the 4th over 4 plus, and again, don't write 5c, just put plus c. So notice, the way I usually do this is I don't actually pull the 5 out in front of the integral, but I just leave the 5 along for the ride here, right? 5 times x to the 4th over 4 plus c. But if you wanted to write it out formally, this is the way that you would do it. Okay, and here's the formal rule. The integral of a constant times a function. Well, how do we do the integral of k times g of x dx? Well, you can pull the k out front. It's just k times the integral of g. So in other words, the k just kind of comes along for the ride. The integral of k g of x is just going to be k times the integral of g of x. So a couple quick examples. What's this one? Well, the answer is going to be 2x to the 8th over 8 plus c. Now, again, you could write it by pulling the 2 out front and writing like this. 2 times x to the 8th over 8 plus c. And again, you don't need to put parentheses here because we're just going to put the plus c on the end. And by the way, this answer is correct. And notice we get the same answer doing it both ways. But we can simplify it. So 2/8 is really 1/4. So we could rewrite this as x to the 8th over 4 plus c. What about this? Well, what's the integral of 5x to the 8th? Well, it's going to be 5x to the 9th over 9 plus c, or 5/9 x to the 9th. plus c. How about something like this? Well, we can rewrite this as 3x to the negative 7th dx. So 3 over x to the 7th is like 3x to the negative 7th. And then the integral is going to be 3x to the negative 6 over negative 6 plus c. And you could leave your answer like that, or we could take the negative up front. Well, the 3/6 is really a 1/2, so the 2 stays on the bottom, and we have a negative up front. This x to the negative 6 can become an x to the positive 6 in the denominator, and this is our final answer. So this is the unsimplified version. This is the simplified version of the answer. So now we're at the point where we know how to integrate any polynomial. So let's do this one here. We have the integral of this polynomial. Well, the integral of x to the 8th is x to the 9th over 9 minus 6x to the 4th over 4 plus 5x cubed over 3 plus, well, the integral of 12 is just 12x and then plus c. Now we could simplify this 6/4 to be 3/2, but let's just leave our answer like this. Okay, now this one is a little bit different because I've given the variable t. Now notice I have a dt on the end here. So we're doing an integral with respect to t, and this is not quite a polynomial because we have t to the 3/2 power and t to the 1/3 power, but it's similar to a polynomial. But it's an integral with respect to t. So what is the integral going to be? Well, the integral of t to the 5th is going to be t to the 6th over 6 minus 10t to the 5th over 5, which that would simplify. That's a t there. That would simplify to be 2t to the 5th. Plus, well, this would be t to the, well, 3/2 plus 1 is 5/2 divided by 5/2, but I'm just going to write it out front as 2/5 plus 12t to the, well, the integral of t to the 1/3 is going to be t to the 4/3 and then over 4/3 or times 3/4. And then plus, now it's tempting to put 7x, right? But it's actually 7t, okay, plus c. Now, again, we could simplify this. This 10/5 becomes a 2. 3/4 times 12 is really a 9. But we'll leave this as our final answer. Okay, and how do we do something like this here? How do we do an integral? Well, we have a product of two functions. It's not true that the integral of a product equals the product of the integrals. And same thing with quotients. It's not true that the integral of a quotient equals the quotient of the integrals. So how do we do this? Well, notice, by the way, we have a different variable here. We have the variable u. But how do we do this? Well, we're just going to distribute the 5u here. So let's rewrite this as the integral of, well, 5u times u cubed would be 5u to the 4th minus 30u du. Okay, so we just distributed the 5u here. Now we're going to integrate this. This is 5u to the 4th. The integral is going to be 5u to the 5th over 5 minus 30u squared over 2 plus c. And let's simplify this. 5 over 5 is just 1. So this is just u to the 5th minus 15u squared plus c. Now, how could we check our answer? Well, we could take the derivative of this. Notice the derivative of u to the 5th is 5u to the 4th. That's this. The derivative of 15u squared is 30u. And so, yeah, we have the derivative of this being this, and that simplifies to this right here. So this was a problem where we needed to simplify ahead of time. Now, that'll be the same thing for this next example. Again, we can't just do the integral of the top divided by the integral of the bottom. That would give us the wrong answer. So how do we do this problem? Well, we simplify first. We're going to rewrite this as the integral of 7x to the 6th over x squared is really 7x to the 4th. 3x squared over x is just 3. And we have 9 over x squared. Now we can rewrite 9 over x squared as 9x to the minus 2. Okay, so we just did this over x squared plus this over x squared plus this over x squared. And we rewrote 9 over x squared as 9x to the minus 2. So this is 7x to the 5th over 5 when we do the integral plus 3x plus 9x to the minus 1 over minus 1 plus c. And we could leave our answer like that. It's sometimes nice to not end up with negative exponents. So let's rewrite this. This negative 1 can actually come out front, and this becomes a minus. The 9 will stay on the top, and this x to the minus 1 becomes an x to the positive 1 on the bottom. So this just simplifies to be this. Now, as we finish up here, you may be wondering, what was the point of all this, right? Why are we doing antiderivatives? And we haven't actually gotten to the point yet. We're just going through this process of doing antiderivatives. Remember, for derivatives, they had to do with the slope of the tangent line. They also had to do with rates of change. And we had all these derivative rules where we learned how to take derivatives, like the product rule and the quotient rule and the chain rule. Well, with integrals, we're also learning how to do these things, but we haven't really said what's the point yet. And we'll just have to wait. Actually, it'll be 2 modules from now when we start seeing what the point of all this is. And we're going to get to something called the fundamental theorem of calculus. But for now, we're just learning this process of how to do integrals.